Welcome to Mythosium, the channel where we take the biggest ideas in science and translate them into clear, intuitive stories anyone can understand. Today we're going to follow a path that begins with Einstein's equations and leads us into some of the strangest, most mind-bending predictions ever made about the universe. These predictions aren't science fiction, and they weren't invented to entertain. They come straight from the mathematics of general relativity, equations that describe space, time, and gravity with astonishing precision. And when you follow those equations all the way, without looking away when things get weird, you end up in a place where black holes freeze time, where white holes explode matter outward, and where tunnels in space-time hint at the possibility of parallel universes. To begin this journey, picture yourself watching a spacecraft fall toward a black hole. As it descends, you might expect it to move faster and faster, accelerating as gravity pulls it inward. But that isn't what you would actually see. From your perspective, something far stranger happens. The ship appears to slow down. Each second of its fall stretches longer than the one before. The light coming from the ship grows redder and dimmer, as if time itself is draining out of it, and, right as it reaches the event horizon, the boundary beyond which no signal can escape, it seems to stop entirely. It doesn't vanish. It doesn't dive inward. It just hangs there, frozen at the edge of the abyss, slowly fading until it disappears completely. Einstein's equations say, this is exactly what an outside observer should see. Time moves differently near a black hole. The deeper you go, the slower time flows. At the horizon, from the perspective of someone far away, time stops altogether. But this illusion is only half the story. If you were the person falling in, time would feel normal. Your heartbeat would tick at the usual pace, your thoughts would move with their usual rhythm, and you would cross the event horizon without noticing anything special at all. General relativity allows both of these experiences to be true simultaneously. From the outside, the fall takes forever. From the inside, it takes only moments. These kinds of contradictions, two realities that both make sense, but contradict common intuition, are exactly what happens when you start letting Einstein's math lead the way. And that math begins with the idea that space and time form a single continuous fabric. Mass and energy cause that fabric to curve, and the curvature itself dictates how objects move. Gravity isn't a force. It's the shape of reality. This wasn't always obvious. For centuries, people thought about gravity the way Newton described it, as a force pulling objects together across empty space. Newton's equations worked well enough to predict planetary motion and falling apples, but Newton himself knew that something about his explanation felt incomplete. He famously wrote that the idea of one object reaching across space to pull on another without the mediation of anything else seemed absurd. But he had no alternative. Einstein did. Einstein realized that what we perceive as gravitational force is simply matter following the natural curves of spacetime. He wrote down a set of equations that relate the geometry of spacetime to the distribution of matter and energy. These equations are compact but incredibly powerful. Even Einstein struggled with them. Solving them exactly is not like solving a typical algebra problem. The equations describe the entire universe, and each solution represents a different possible universe with its own rules and structure. The first exact solution was found not by Einstein, but by a German physicist named Karl Schwarzschild. While serving in World War I, Schwarzschild considered the simplest possible scenario, a perfectly spherical, perfectly still mass surrounded by empty space. When he solved Einstein's equations for this setup, he discovered something bizarre. At a certain distance from the center, a distance now called the Schwarzschild radius, the equations behaved badly. One part of the solution went to infinity. At first, this seemed like a meaningless mathematical artifact, but as physicists studied Schwarzschild's solution, they realized it revealed something extraordinary. That radius was the point at which escape velocity, the speed needed to break free from gravity, equaled the speed of light. Outside that radius, light could escape. Inside it, not even light could get out. A boundary had been formed, a horizon that nothing could cross outward. This wasn't just a curiosity. It was the theoretical birth of the black hole. Not everyone accepted it. Einstein himself believed nature would somehow prevent such an object from forming. The idea that matter could collapse so completely seemed to violate common sense. But nature does not follow common sense. Nature follows mathematics. And when scientists studied the collapse of massive stars, they discovered that once nuclear fuel is exhausted, nothing stops gravity from crushing the core. If the star is massive enough, no known physical force can halt the collapse. The result is a region of spacetime so curved that every path leads inward. A black hole is born. To understand what a black hole really is, it helps to use an analogy. Imagine space as a river flowing toward a waterfall. Far from the waterfall, the current is gentle. You can paddle away easily. Closer to the edge, the river flows faster. At some point, the current becomes stronger than you can swim. Even if you try your hardest, you're swept along. That point is like the event horizon. Beyond it, the flow becomes stronger still, and eventually even light, the fastest thing in the universe, is dragged inward. Inside a black hole, space is flowing faster than light toward the singularity at the center. This picture captures something essential. Nothing inside the horizon is moving faster than light relative to space. Instead, space itself is moving faster than light relative to everything inside it. That's the difference between violating physics and bending physics to its limits. But as strange as black holes are, Einstein's equations reveal something even stranger when you flip them around. If you take the solution for a black hole and reverse the direction of time, you get an object that behaves in the exact opposite way. Instead of pulling matter inward, it pushes matter outward with unstoppable force. This object is called a white hole, the theoretical mirror image of a black hole. Nothing can fall into a white hole. Everything is expelled from it. No experiment has ever detected one, and it's unlikely they exist in our universe. But Einstein's equations say they could exist. They are mathematically allowed, even if the universe doesn't seem to use that option. But the real surprise comes when you connect these two solutions, the black hole and its time-reversed counterpart. When the math is extended fully, it forms a kind of bridge, a tunnel through space-time known as a wormhole. The simplest versions of these wormholes are not long tunnels like in science fiction. They are incredibly short, pinched structures, more like two mouths touching for an instant. In theory, this bridge could connect two distant regions of space. In theory, it could even connect two entirely separate universes. But there's a catch. These wormholes are not stable. They collapse faster than any signal or traveler could pass through. The bridge forms and collapses in a blink, never staying open long enough to become a usable shortcut. Still, the math doesn't stop there. When scientists explored solutions that describe rotating black holes, called Kerr black holes, new possibilities emerged. A rotating black hole drags space-time around with it. Near the black hole, space itself begins to twist, sweeping everything along. There is a region outside the event horizon called the ergosphere, where space-time rotates so rapidly that nothing can remain still relative to the stars. Inside the rotating black hole, things become even more surreal. The singularity, the central point where the equations break down, is no longer a point. It becomes a ring. A ring singularity opens the door to mathematical paths that avoid the singularity entirely. A traveler falling in might slip through the ring and emerge somewhere else. It might be another part of our universe. It might be a different universe entirely. It might be a universe where time flows backward relative to our own. If you follow this mathematical maze all the way, you end up with a structure that repeats endlessly. Black holes, white holes, bridges, and universes stacked together in an infinite chain. Each black hole contains a universe. Each universe contains black holes. And the pattern continues forever. This sounds like pure fantasy, but it's a direct consequence of taking Einstein's equations to their logical endpoint. Whether these parallel universes exist physically is another question. Real black holes spin. Real black holes emit radiation. Real black holes form from collapsing stars. And when you include quantum mechanics, the perfect mathematical wormholes of general relativity collapse into singularities before anything can pass through. But even if wormholes never become bridges we can travel through, the fact that they appear in the math at all tells us something profound. General relativity isn't just a tool for predicting the motion of planets. It's a window into the possible shapes that reality itself can take. It hints that the universe we see might be only one version of what spacetime can become. Einstein's equations describe a universe where time slows, space flows, tunnels appear, and distant realities may exist beyond our cosmic horizon. They show us that the universe is not a rigid stage, but a flexible, dynamic fabric capable of bending in ways that strain our imagination. And perhaps the strangest part of all is that these ideas, the frozen fall at the horizon, the flowing river of space, the possibility of parallel worlds, weren't invented for storytelling. They were discovered by following the logic of mathematics, wherever it led. That's the beauty of physics. It doesn't just describe what we see. It reveals what we never could have imagined on our own. If you enjoyed this deep dive into the hidden geometry of the universe, make sure to subscribe to Mythosium. Here we take the biggest mysteries of science and make them vivid, intuitive, and unforgettable. Stay curious, and I'll see you in the next exploration.